therefore ensure that you are able to derive that equation. But I want to believe it's something that we have already covered in our classes. Therefore, we are just trying to remind ourselves and revise. That is why next, after the inclined plane, we go now back to, remember, for mechanical advantage, it remains load over effort. Now, with the wheel and axle, where do we normally have, in reality, where do we normally have wheel and axle as a machine? Somebody, where do we come across wheel and an axle as a machine?
In wells.
In?
Let's say a flag.
I can't get what you're saying.
Flag post.
Flag post?
In a well.
When drawing water from wells.
In a well.
Drawing water from wells? Where else?
Yes.
Now, so when we look at a wheel and axle as a machine, we have two wheels, the large wheel where we apply effort, and the small wheel where we apply the load. Now, in one complete revolution, that is, the wheel moves through a distance that 2 pi r, while the load, that is the effort. Where we apply the effort is the wheel. It covers a distance of 2 pi r capital, while where the load is attached, and normally the load is attached on the smaller wheel, it covers a distance of 2 pi small r. Now, therefore, our velocity ratio, the distance moved by effort, divided by the distance moved by load, we end up with the capital R over R. That is for velocity ratio. I remember I said for mechanical advantage, all the machines, it remains the same. That is load over effort. Velocity ratio is what will keep on being determined differently depending on the machine that you are using. Let's try that example for wheel and axle, and then we'll try another one for inclined plane. Let's try that question.
Madam, allow me to interrupt a bit as they are doing the question. Could you ask them to mute? We can hear someone eating in the background. Let them mute their videos and audios.
Okay. Let's try that example. At least 2 minutes should be enough.
kwamba jioni project yako file. And something else. Na sasa sasa ndio alikuja kwetu nyumbani. Sasa ni 7 times. Na is good. That is good. Unajua sasa ile yetu kukula pale jioni ni pale kwangu.
I can see a few answers here. Mechanical advantage, Terence 6, velocity ratio 8.5. Victor Kibet. I don't know whether this one is for this question, 70.58%. Ryan Duku.
Mechanical advantage 6.
Huh?
Velocity, mechanical advantage 6.
Mechanical advantage 6.
Velocity ratio 8.5.
8.5 velocity ratio.
Efficiency 70.59%.
70.5. Any other answer? I can, okay, let me look at the charts. Sean 6, velocity ratio 6. Mechanical advantage 6, velocity ratio 8.5. Efficiency 70. I think, okay, let's look at the working then. That's our working. Mechanical advantage 6, as people are saying. Velocity ratio, that is the working, 8.5. And efficiency 70.59. I think ensure that you try these examples or look for more examples and let me get an example for an inclined plane. Yes, can we try that for an inclined plane? Let's try that for an inclined plane. I can see somebody with the effort 756.1 Newton. Anybody else? I can see effort 756, 756, 756, 756. What about part 2? Part 2, part 2. Part 2, the work done against friction in raising the load through a height of that. Okay, against friction, 1,409 joules. That is from quinoa. But he got effort as 1,176. We will see the working. I can see somebody else with a I want to believe this is part A, the work done. 133, 113. So can we look at the working? Let's look at the working. So we were to look at mechanical advantage. We were to look for that is the formula is efficiency there. Let me go take you a bit back. We have been given the efficiency of that inclined plane to be 85. And the angle of inclination is 40 degrees. The load to be lifted is 100 kilograms. Remember, you can't work with kilograms. I hope nobody worked with kilograms. You have to change that into a force. So when you come, the working there, one over sine, oh, mine is talking about 50. Just a moment. Yeah, the angle is 40. So this should be.
Actually, it's okay.
Huh? No, I'm changing the angle. I'm just changing the angle. Mine was typed wrongly. Sine 40 degrees. So looking at the working there, we have is mechanical advantage. Did you get mechanical advantage as 1.1?
No.
What do you get as a mechanical advantage?
1.275.
1.27. I want to believe mine. The example had been worked out with the sine 50. So the effort therefore then James Macharia, yes, I don't know whether your hand is up or
I think the angle should be 50 because the question was saying that it made an angle of 40 degrees with the vertical.
Oh, let me just go back. The inclined plane makes an angle of 40 degrees with the vertical. Oh, yes. Yes, it remains 50. Yes. That's correct. I don't know. I just... So our effort is that. Do we agree that our effort is this? What is on the working? Hey, are you people there or you're not there?
We are here.
So I'm asking, is this answer 900? Looking at my working, because you are supposed to have looked for mechanical advantage. And according
Yes,
to
the answer is
my
900.
working, the mechanical advantage is 1.1. I hope that's what you got.
Yes.
Yes.
Yes?
Yes.
Yes.
And when you got mechanical
Yes.
advantage, is load over effort. Remember, I indicated do not work with 100 kilograms. You are to convert 100 kilograms into weight, which is multiplying it by 10. So you end up with 1,000. So when you substitute your formula, effort will be equals to 1,000 divided by that. And our answer is effort is 900.9 Newton. I hope we can see that clearly. Then when you move to part two was talking about, let's go back to the question, work done against friction in raising the load through a height of that. So, who can explain where 15% is coming from? 15% of work input is used to overcome friction. Where did we get that 15%? There's somebody, if your mic is on, please, can you mute it because I can hear the background? Abdi Malik, Mohammed, you have raised your hand, yes?
Effort time is distance moved by the effort.
Huh?
Effort time is the distance moved by the effort.
No, I'm asking, where does the 15% as work input? If you look at my working, 15% of the work input is used to overcome friction. So I'm asking, where do you think the 15% came from? So I wanted someone to explain to us where that is. I can see, I can't see the names of the people who have raised their hands, but I can see 5 people have raised their hands. But on I can't see who they are. Okay, Bibi.
So, madam, if I'm okay, to me, I can say that the 15%, we say that efficiency can't be 100% due to friction. So that's why it is 85%. So the 15% comes from subtracting the 100% with 85% due to the friction. So that the
Yes, the 15%. Remember, the machine was 85% efficient. So definitely the 15% went into overcoming the what? The friction. That is how the 15% comes about. Good. Therefore, the working is shown there. And our answer is 1,411.26 joule. Is that what we got? Did the people get that?
Yes.
I think the deduction of the efficiency 100%, energy lost by friction is supposed to be sine 50. Yeah, I can see the people have, yes, those who have written it down, I agree with what you have written. And then we move on fast. I can see, because I wanted you people to do another topic today. That is the next hour. We move on to the screw as another machine. The distance between two successive threads of a screw is called the pitch. And on the diagram, it's shown clearly what the pitch is. Mechanical advantage remains the same, load over effort. Velocity ratio is the circumference of the head. That is the distance moved by the effort over distance moved by load. And in this case, the distance moved by effort is the circumference of the screw head, which is determined by 2 pi r. And the distance moved by load is the pitch, the distance between the two threads of a screw. That is the pitch. So looking at that, that is what we have. That is how we determine the velocity ratio of a screw. Now, a screw can also be combined. Okay. A screw combined with a lever is used as a jack for lifting heavy loads. I want to believe you have seen that. The jack of when you're lifting, when you have somebody has got a puncher. So that's an example, but we not look at the example, but this is what I'm talking about. So the handle here has been added to the screw, and therefore now what you're having is a screw combined with a lever. This is a screw combined with a lever. We will not look at the example. We look at it. Okay, we'll come back. Just I want to finish so that we don't go back to this topic again. The next machine is the gears. Is the gears. I can see somebody writing something here. That is the gears. We have the where we attach the load, and where we apply the effort, and where we attach the load. Where we apply the effort is normally referred to as the driver wheel. And where we put the load, or where the load is attached, is the driven wheel. Normally the driven wheel is smaller in size as compared to the driver wheel. That is, it has got less, what are they called? Those, just a moment, let me show you what I mean. I'm talking about this, what are they called, these ones here?
Teeth or cogs.
Teeth.
Yes, these ones here.
The teeth.
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 Yes.
Okay, those ones. Now, in that case, the driven wheel has got less as compared to the driver. This is the driver. It has got more of those, what I don't know, you're calling them teeth or what.
Teeth.
So in this case, therefore,
Teeth.
normally, where you're applying the effort, let me just take you back. Where you're applying the effort must always, the wheel must be larger than the one where you're attaching the load, because you need to make your work easier. And if you have to make your work easier, and the only way is to ensure that where you're applying the wheel, with the moment where the effort is being applied covers a longer distance, then the smaller wheel will make more revolutions. I can see the Mr. Biro indicating that we do roll call.
Yes, please connect to roll call. Just look at your screen, boys. You can see the display. Pick your class and submit.
Roll call.
We are now at 130. I can see 140, 150. I've done the roll call. I can see 160. I've done that. Out of about 200, I can see we are at I think 170 now. And 70, that is about 87% of you have done the roll call. The others who had indicated yesterday they cannot see the roll call. We said you update your application, update your Zoom app. If you're using a phone, you go to the Play Store and update your software. If you're using a laptop, try updating because any updated, I think, software should be able to be compatible with the roll call feature. That. Select that. Take the roll call. We are at 179 now. 180. At 92%, I think we can 93% now. I think that can bring us to the closure. Just a minute. Yeah, 94%. That is 184 out of 195. This is quite okay. Thank you very much. We end the roll call now.
Okay. Yes, we were looking at the gears. So I am there. The velocity ratio, remember, is distance moved by effort divided by distance moved by load. Revolutions made by the driver wheel, or the number of revolutions made by the driven wheel. That is the most important thing. This part, remember distance moved by effort. Where do we apply the effort? We apply the effort at the driver wheel. Where is the load? The driven wheel. The moment you know that, therefore you know velocity ratio, revolutions made by the driver wheel over number of revolutions made by the driven wheel. When we divide that, we end up with the number of teeth in the driven wheel over the number of teeth in the driver wheel. I hope Mr. Owino will give me a few minutes. We might not be able to do examples. I want us to just cover a bit of the pulleys. Yeah, a pulley is a wheel with a groove for accommodating a string or a rope. Now, the velocity ratio of a pulley system is the number of ropes supporting the load. That is very important. Normally, when you're determining velocity ratio on a pulley, you count or you determine the number of strings that are supporting the load, or what we call number of strings under tension in lifting the load. If you are able to identify the number of strings under tension when lifting the load, then you are headed in the right direction. So we have the first type of pulley, that one, a fixed pulley. We have the load, the effort. Another example, the next one is where one. A single movable pulley, but there are two types. If you look at the first example, the velocity ratio there is 2. Even the second one, the velocity ratio is 2. But the first one has got a single pulley, which is movable. And the second type of pulley has got 2 pulleys. One is movable, one is fixed. When you're counting the number of strings, let me just show you again. If you look at this one here, this string is under tension. This one is under tension. And the effort string is acting upwards, therefore it is under tension. And therefore that means the velocity ratio there is 2. When you look at this one here, this string is under tension. This one is also under tension in lifting the load below, but the effort distance is not under tension, is acting the opposite direction. So the velocity ratio in this case is 2. Note, when you're drawing your diagram, this string here must be taut. I don't know whether how to pronounce it. Kizungu. Let me just write here. This is what I mean. Yes, that one. Is that one? Oh, yes, I believe so. So these strings must be under tension or taut. Please let them not curve. Do not curve the strings when you are drawing. If you do, you lose marks for that. If you are told to draw the diagram to show, and you draw a diagram, normally people draw something like this. Somebody draws a curve which is like this. Curving. That is wrong. That is wrong. It must be straight. Like what is on my diagram. The next one is that one, the block and tackle. This consists of 2 or more sets of pulley blocks. We have examples. In a pulley and in a block and tackle, we have movable part of the pulley system and another one which is fixed. And normally they are a set of 2 or more. Like this one here, we're having 3, here we're having 4. So counting the number of strings under tension, for the second one is velocity ratio is 4. The other one, the velocity ratio is 3. For block and tackle, with an odd number of pulleys, it is convenient to have more pulleys fixed than movable part. This is an example of that. Just a moment. This is an example of a pulley, this one here, of odd numbers. There are 3. So we are being advised that ensure that more pulleys are on the fixed side and less on the movable part, because the lower part, this part is movable. This part here is fixed. But if they are equal like this ones, you just divide an equal number. I don't know if Mr. Owino is around in our class.
Yes,
Oh, you are there. Just give me a few minutes. I finished. Thank you.
yeah, just finish.
Okay. So up to there, I think the others are examples. Pulley belts. Where do we normally use our pulley belts? Or where do we come across a pulley belt?
Bicycles.
Bicycle.
A what?
Bicycle.
Yeah, bicycle, a
Social
sewing
media.
machine. And velocity ratio for a pulley belt, that number of revolution. Remember, for a pulley belt still, the effort is applied on the larger wheel or the bigger wheel, and the load is attached to the smaller wheel. We have been given their examples. They are found in portion mills, sewing machine, motor engine, etc. And that is how we determine the velocity ratio. of a pulley belt. I'm trying to rush so that we can cover something else with Mr. Wino. And then we have the hydraulic machine. You go remember your topic for pressure in form 1. It's a very important topic. I think maybe I can stop there so that what is remaining is the pulley belt, is the hydraulic machine. I think I can stop there for now so that Mr. Wino can come in and start what he's supposed to do. I want to believe that today's lesson was better than last week. And for last week, I'm sorry for that. I had challenges about a few things and there. Okay. Mr. Wino.
Yes.
Yes, I want to believe I'll give you now to start.
Yeah, thank you. I joined late, but I've enjoyed the lesson. I hope the students have also enjoyed.
Yes.
Okay.
Yes.
Very much.
It was a nice
So I think
presentation.
you can start. You are doing which topic, Mr. Wino?
I don't know. Or they have a suggestion. I wanted to do Newton's law, unless they have otherwise. They prefer another one which they feel that much more, they need more work maybe to be revised on, if in any case they have.
Okay.
So maybe just you can still be there, no problem. You can just go to the chat box and I mean the students now. Get to the chat box and let me see if you are okay with proceed the Newtons, or there's another topic you would prefer. Maybe we want to do Newtons, and yet maybe the Newtons you understand better. So if there's another one, kindly talk to me in the chat box.
Can't message you.
Do Newtons.
Madam Oeri, you can check your chat box because you are the host. You are the host, so messages may be coming to your chat box. Kindly check.
Mr. Mbiro should make you the...
Look at what they're saying in your chat box. Maybe that message is sent there.
Newton's law. Newton. I think most of them are talking about Newton. Okay, there's refraction, but I can see Newton is the higher percentage. Newton.
Okay, good. If most of them are saying we do Newton, then I think that's what we'll go by, the majority. So I think our prediction was correct. Yeah, we can just go with the Newton. So I think I'll still be able to, let me see if I'll be able to share if I'm not the admin. I think it allows. Maybe if Mbiro comes in, he'll be able to make me the co-host. Or you can assign the role to me, it's possible.
Is it possible?
Yeah. If you go to the part of leave, I think you can, there's a way you can reassign the role.
Allow all participants to...
No, don't. Okay, Abdimalik Mukhtar, you can mute kindly. Good. So let me just begin as we sort out that later. So I'll just be sharing my screen. Of course, for me, I like writing as I present, so I will not give you a PowerPoint. I'll give my screen. And then I prefer writing. Yeah, it's easier on this. So you can confirm, you can hear me. The screen is also visible for you.
Yes.
Yes,
sir.
Good. Now let's now continue with the beautiful study of physics. As animalists say, the beautiful, the most easy, and the most interesting science. Because it allows us to understand how nature works. Now, you know, the quest of people always very curious. Actually, generally it's called natural philosophy. You always want to know what's happening, what's going on around you, and such like stories. So people were most interested in understanding the ideas and everything that were happening. And thank God, in the early, I think the early 17s therein, came the scientist Newton. Of course, the work that he was doing had been done by some, had been at least somehow written down by some people, like, you know, his predecessors like Galileo Galilei and other people were also able to come up with this kind of ideas. But later on, it is him who, that is Isaac Newton, who was able to come back and redefine them, restate them, and state up the laws of motion. And that's why the topic of the laws are still called Newton's laws of motion. Actually, they can just be laws of motion, but we are used to call it the Newton's laws of motion because he's the one who coined them up and then wrote them as the three. So in his honor, it is important to still regard him. So the Newton's laws of motion are basically three of them. And the main aim of these laws is basically to describe for us how the motion of our body takes place. Of course, you have done in topic 1, linear motion. We are doing the study of the motion without considering the force that was causing it. We were just studying it generally. But now when we get here, we're now interested that that motion that was happening, what was the cause? And if in any case there's something is in motion, if you apply another force, what happens? If something's at rest, we were saying that an object begins from rest to a certain speed. How or why? There must be a force that was applied. And that is now where we use the Newton's laws of motion to do that. And in case something is moving, you can change its direction, you can stop it, and all those stories. Newton's laws is able to explain. Some of the things that are going to apply here, of course, we're going to look at Newton's laws of motion, the 3 laws of motion. After that, we shall be able to look at, after looking at the laws of motion, we shall be able to look at maybe the friction, And we'll be able to look at both the frictions and the dry and also the fluid friction. So the one that is acting in solid surfaces and the one that acts in fluids, like basically what you call viscosity or the viscous drag. So that is the aim. The laws of motion are actually three of them. You have the first, the second, and then the third law, like that. So in the process, we shall look at some other applications, like for example, when you are in a lift, how do you feel the weight being exerted, the reaction, how is that, and all those other stories. So without much further ado, I can begin with the Newton's first law of motion. So Newton's first law is actually one law that you have been doing it indirectly anyway, indirectly all the way from when you're in primary. Actually, these laws have been doing them indirectly all the way when you're in primary. Because if you check, one of the effects of a force is that it can initiate motion. It can make of course, it can initiate a motion. That is, if the object was at rest of course, it can be made to start moving like that. So that's an effect of course, that's an effect of force, and that is what Newton's first law is talking about. And we all agree that if at all you leave something, assume that nothing takes place, like an earthquake, or maybe you leave a book in a room. That book will stay there for the longest. It will not move anywhere because there's no force to push it. And by the way, another interesting thing is that for those who know how to cycle, if you are to cycle and you are in motion, so you're already in motion. If you don't apply any force, let's say the brake, and assuming that there's no friction forces at all, you can move that bike forever, by the way. Are you aware of that? Actually, if you ignore friction, you set something to motion. Let's say that you take a ball and that ball start moving, and assuming that there's no friction and there's no other force that is acting on that body can continue moving forever without stopping. That's interesting. That's the power of the Newton's first law of motion. But normally, in most cases, when something is moving, apart from the external force you may apply to stop it, there's always also the normal frictions that happen here and there to make sure that the motion is retarded, or it is decreased, the speed and all that, until the body finally comes to a stop. So Newton's first law of motion, again, we experience it many times when you are in a vehicle and maybe the vehicle was at rest, then it starts to move. You'll feel like you're being jerked backwards, of course, because you want to remain the way where you are. Of course, if the vehicle is moving, and of course, when a vehicle is moving, let's say that the vehicle is moving at a speed of 20 meters per second. Everything inside the vehicle is moving at that speed, including you. Including you. And that explains to you another reason why, if you are in a vehicle and you have not put on a seatbelt, you have not fastened a seatbelt, when the vehicle stops abruptly, you'll be surged forward, you'll move forward like that. So that because you are moving at this speed, and you always want to continue moving at that particular speed. So it is interesting, of course, how this Newton's first law talks about. And this Newton's first law is very powerful. It tells us something, that if you are in a, somebody's talking, or you are, is there a question?
No.
Any question? We are okay?
Yes.
Okay. Now, this law is very powerful. It also tells us this, actually, that if you are, now this one here was telling some people and they were refusing, that if you are in an open track, if you're in an open track, let's say that is a track, you're in an open track like that, and you are at this point, let's say you're at this point here, and a good approximation, assume that nothing goes vice versa. If you jump up, the track is moving, of course. If you jump up, so that after some times, the track imefika hapa. Let's see that the track is already somewhere here. The track is moving. And you will hautaanguka chini. How many agree and how many disagree? You
We
won't
agree.
fall. You will.
I agree.
Jabba.
I disagree.
I disagree.
I agree.
Ukweli mwalimu.
Hakuna kitu.
Kwa kitabu ni ukweli, lakini real life we.
So the reason is because when you are moving up, let me explain. Are you still able to hear me?
Yes.
No.
Oh, you can't hear me?
We can.
We can hear you.
All right. So the reason is this: when the truck is moving, as I said before, less than 20 meters per second, then you are also moving at that particular speed. So that when you jump up, what happens that you end up setting yourself into a horizontal projection, actually. So you'll be moving like this, evil, like that. And remember, if you do that projection, so you'll be moving this way, then like that. The same as when you throw that stone up. If you throw that stone up, it end up setting itself into this particular projection like that. So that's what really happens in the process. So you will not really be where you are, but you'll also have moved forward because you had a horizontal velocity as well. So, and this explains why if this thing was to stop abruptly, you'll move forward because you're also traveling at that particular speed. And if you are just, everything was at standstill, was at rest, then the truck starts moving all of a sudden, you may end up falling because you want to maintain the initial state of motion. So that's what Newton's first law is all about. He said that a body will remain in its state of rest. So let me write it here. So a body, let me write it here. That a body will remain in its state, remain. No, it's not coming. You're not writing well properly. Let me erase. So a body will remain in its state of rest, or remains in its state of rest, or uniform. So I don't know why it's not writing well. But you're still able to see the screen.
Yes.
In its state of rest, in its state of rest, its state of rest. So I'll just state it, then I'm just writing it. It's not coming out well. I don't know what's up with the screen. The rest or uniform motion, or uniform motion. So uniform motion. So if it was moving, it should remain that particular motion unless acted upon by an external force. Now, why an external force? It is important to clarify an external force because when the body is already moving, there may be a force that's already being applied. So you don't want to confuse these two things. Yes, I know for a body at rest, the forces have cancelled out actually. That's why it is at rest. And therefore, any force that comes in is enough to change the motion as Newton's first law demands. But for a body that is already moving, there's a force that is already in motion. So if you want to do the stopping or do anything to it, maybe for it to change direction so that it doesn't move in a straight line, or maybe you want it to stop, you must apply an external force. And that is what Newton coined as the first law. So that is that. But nevertheless, of course, this one we may not always experience it in a real case because of other things, as I said, like the frictional force, the air resistance, etc. normally affect our motion. So this tendency, generally, this tendency of a body to remain in state of rest is what we normally call as inertia. Inertia. And now we normally explain that inertia most of the time. And that's why it is important that when you are using maybe a vehicle, you should always put up, you must always fasten your seatbelt just for safety. So that is the law. So that's the idea was their tendency of something to remain, of course, that nice. So basically, of course, the inertia measures basically the mass, how heavy the body is. So the amount of that depends on how heavy the body is. Yeah, like that. So the idea of Newton's first law comes to us with something that you need to understand now straight away before we go to the Newton's second law. So that's the Newton's first law, just simple like that. Now I need to go to the Newton's second law, but still I need to follow up this keenly. Assuming that now we have followed this our Newton's first law. Suppose you now apply a force on something. So the body is moving, of course, and we don't want to continue that uniform motion. We want to apply a force. We want to bring in our Newton's second law of motion. So if you apply a force, what happens? That's what Newton's second law is now all about. The first law is telling us, let that body rest where it is. Let that body stay in motion. But in case a force comes in, what happens? That's what Newton's second law is now telling us about. And before we go to Newton's second law of motion, there's something we are going to use, which is called momentum. Momentum. And momentum is a quantity that every body possesses. Whether a body is at rest, of course, if it is at rest, the momentum will be zero. But anybody that is moving must always have that quantity called momentum. And of course, momentum is basically defined as the product of mass and velocity. So if you're looking for momentum of a body, let's say the body is moving at a certain speed, you want to find its momentum. It's just mass times the velocity of that body. And from here, you can see straight away that both momentum, of course, will be bigger if the body is much heavier. That is, if the mass is much bigger. Similarly, the momentum of that body will be greater if the body is moving at a higher velocity. And we are going to see the power of this one later on when you look at now Newton's second law and maybe look at the impulse and the impulsive force and the effects. When this happens, when an accident happens, what really happens when you are moving at a high velocity? You are going to see how the momentum is going to play a very big role in that case. So it is a product of mass and velocity. And of course, the SI unit we can find straight away as mass is kilogram, velocity is meter per second. So the SI unit of momentum will be kilogram meter per second. Kilogram meter per second, and that is kg m per s, like that. So this a vector quantity, it has direction, of course, and the direction of momentum is always given by the direction of the velocity. So the direction in which the velocity moves in the direction of that momentum. So if the body is moving towards this direction, so the velocity is towards that direction, then the momentum is also directed towards that direction. So momentum normally denoted by the letter P, so the P will be in that particular direction. So small letter P, the capital P is for pressure, so the momentum can take the small letter P. That is linear momentum, because those who have angular momentum, it has a different letter to represent it. So for the linear momentum, we represent using that. So that is the idea of momentum. I don't know that I should give an example. I want to assume that is direct. Direct. I don't need to give an example. If you're having a mass, let's say you're having a mass of 50 kg, we're moving at a speed of 10 meters per second. Your momentum is just 50 times 10, and that is 500 kilogram meter per second. So I hope that idea of momentum is okay, so that we can see how we use it. So is the idea of momentum okay? So let me see, it's like yeah, there's a question that I directed earlier on. What if the track is accelerating? In that case, you risk. In that case, you risk, because it shall have increased at some speed anyway. So somebody also gave us the law, and that is okay. There's also somebody who had asked me, because of the Newton's first law, does it mean that if the Earth stops rotating, suddenly everything will be thrashed eastwards at 80 miles per second? That's very true. By the way, the Earth, as we see right now, as we are racing right now, it is at a very high speed rotation, very, very high speed. And if it was something was to happen, so that it just stops abruptly, you will accelerate at a very high speed, very, very high, until you'll even die within a few seconds. That's very, 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 very true. If the Earth was to stop rotating just right now, whatever will happen will be serious. Will be very serious. That's the power of this Newton's first law. Anyway, but things are stable in the universe, at least for the next million years, at least, or so. These things will be stable. Maybe things can become chaotic after some many years. We want to be there. Okay, so Newton's second law. Now, if I go to Newton's second law, Newton's second law. So if you go to Newton's second law, now it's about that body, the same body that was moving, but now suppose we apply a force. The force will increase the speed of this body, of course. And when the speed increases, what happens is that the momentum must also change, because the body was moving initially with a certain speed and it had a certain momentum. So when you apply a force, this work will be to accelerate probably, or maybe decelerate, whatever happens. So suppose that the force is to accelerate, so that it increases speed. So what happens that the body will start moving with another velocity, which may be higher than the previous one. So in that case, we have had a change in velocity, and that is corresponding to a change in momentum. So the amount of change, that change of momentum you're going to have when you apply a force on that body that was initially moving, will be proportional, will depend on that force that brings that change. So if the force is big, the change in momentum will also be big. If the force is small, the change in momentum will also be smaller. And of course, it must be the same direction. If the body was moving this way, then another force is being applied in that particular direction, like that. So the change in momentum will be still in that particular direction, of course. So it has to take place in that particular same direction. So this gives us the formal definition of the Newton's second law, and it simply tells us that the rate of change of momentum of a body, the momentum of a body is directly proportional to the resultant external force produces a change and takes place in that direction of the force. So this simply means that the force is supposed to be directly proportional to the rate of change of momentum. Rate of change. So it's about change in momentum, but of course, this takes place within a certain period of time. So we divide this by some time. And because we're talking about a rate. So when you talk about rate, of course, it's a time rate. So divide by time. So this is the proportionality that we have. That force, you apply a force, the change momentum will be there, of course, after some time. And that are always proportional. So let's see, how do you find change in momentum? Change in momentum will be equal to the change in anything is always the final minus the initial. So the final momentum will be the mass times the final velocity, then minus the initial momentum, which is mass times the initial velocity. So it will be mass times the final velocity minus mass times the initial velocity. Notice V is small letter, M is small letter, M is small. Everything here is small letters. MV minus MU. That's the change in momentum. So we can come back and now write our relationship in a much better way. Sorry, we can now have it this way. So our F is proportional to this actually. MV minus MU over that T. And I want us to focus on the right-hand side, and we see something familiar. We can factor out M, so that we are going to have F will be proportional to M into V minus U over T, like that. And then we see something that M, this one here, leave a lot M. V minus U over T is something familiar to us. It's an acceleration. And therefore, we can write that our F now needs to be proportional to M, MA, like that. And so at this point, if we want to remove this thing, I don't know that you have done variation, formula and variation in mathematics. Have you done that in maths?
No.
Oh,
Z.
Not
but
yet.
maybe you did this idea when dealing with the
No.
gas law chemistry. Anyway, there's a proportionality here. So there must be a constant of proportionality. A constant of proportionality must be there. So if we have to remove this proportionality symbol, we have to replace the equal sign, but then now bring in a constant, let's say K, then MA, because of that proportionality. We don't know how these things are proportional. But then, if we look at the definition, of course, where K is just a constant, so K is just a constant, and we are going to see that this constant is supposed to be equal to 1 because of the definitions that we have. We know that if a force of 1 Newton, of course, will produce an acceleration of 1 meters per second if a body is of 1 mass, is of 1 kg of mass, like that. So if you let everything be 1, 1, 1, then the K becomes 1, and then F becomes equal to MA. And these are very powerful and very important formulas of all time. Actually, this is the most famous known equation of Newton. Okay, like mostly in we're dealing with mechanics, and that is dealing with the normal motions. If you don't go to Mambona, the gravitations, because he also has a law in universal gravitation there. But this one here is a very fundamental one, and this is what guides. This is a second law actually, and it guides most of the motions. When you do an acceleration of a body, when you do a deceleration of a body, when something is moving, you can always play around with this. If you want to produce more acceleration, this demands that the force needs to be greater on the same body. Or vice versa, if you have a bigger force on the same body, it will give a greater acceleration. And this very, very important formula. So Newton's, if you're dealing with the equations, this is always what we will be talking about. We'll be saying that from Newton's second law, F is equal to ma. From Newton's second law, F is equal to ma. But then if asked definition, at least for the sake of your high school syllabus, just restrict to the other one. Actually, this also should be the correct definition of Newton's second law. This is a Newton's second law, of course. But according to our syllabus, our curriculum, we restrict to that initial definition. So we'll just be using this, but the definition remains the other one. The one that talks about rate of change of momentum of a body is directly proportional to the external force, of course, that is causing that change and acts in that particular direction of that force. So that's a very fundamental, very beautiful thing. Maybe for this, I can give a small example. You can give a small example on how to use this. So an example is this. Now, before I go to the example, any question? You know, understanding the concept is always much more important than even solving all this. So the idea of that is okay. Let me observe. That idea of Newton's second law and that idea of change in rate of change of momentum. Rate, not changing. Change in momentum is something else. So rate of change of momentum is what we're dealing with. So example, a body. So you can just write a body of mass. A body of mass 500 kg. A body of mass 500 kg is traveling at a speed of, so initial velocity is traveling at a speed of 30 meters per second. A body of mass 500 kg is traveling at a speed of 30 meters per second. We'll stop. It is then, brakes are applied, and is then brought to rest. It is then brought to rest in 6 seconds. It is then brought to rest in 6 seconds. So determine the braking force. Determine the braking force. Determine the braking force. So by the fact that it comes to rest, it gives us the final velocity to be 0 meters per second because it is coming to a rest. So this is the data that we have. The mass is 500, initially at 30, time is 6, then V is 0, like that. So we want to find the braking force. the braking force. So let's find, you can do it systematically. We know that the force is supposed to be given by MA, that is from the Newton's second law. So the mass of the body we have, so we need to find the acceleration. So acceleration is given by the rate of change in velocity, V minus U over T. And then this will give us, V is the final velocity. So don't alter, just write the way it is, 0 minus. It will come with a negative because actually the body is retarding, or the body is decelerating. So U is 30, then divided by T, which is 6. So this will give us, is it -5? So -5 meters per square second. That is the acceleration. So if us to find the acceleration, of course, it is -5. If us to find the deceleration, it is 5. The word deceleration already represent a reduction, that is. The word deceleration already represents that is reducing. So just put with 5. But if the question asks you to find acceleration, we need to see the negative to tell us that it is a deceleration. So from there, you can now put it here in our equation. So our force was equal to MA, and the M is the mass of that body, which is 500 times -5 times -5. And then this will give us -2500. So -2500 newtons, like that. So I have a question. Should we leave the answer with the negative, or we should take the positive of the answer?
Negative.
And why should it remain that way?
Choose the direction of the force.
Excellent. It has to remain as negative because it is showing the direction of the force. Force is a vector. And remember, if the body was moving, let's say that it's moving in this direction. Let's say the body was moving in this particular direction, like that. Then for us to stop it, we have to apply a force of friction. Like this case, it's a brake. The brake will be acting in the opposite direction, and that's why it's coming as a negative. It's something which is retarding. It's a retarding force, the force that opposes our original motion, and that's why it has to come with a negative, like that. Unless if asked to find the magnitude, if you're told to find just the magnitude of the retarding force or the magnitude of the frictional force, without the braking force, then in that case, you now ignore the negative and talk of 22,500. If asked to find the magnitude, because magnitude simply means the size. But if asked to find the force, force is a vector, so you also need to know which direction is it moving, apart from knowing that it is 2,500. So let me check if there's any question before we proceed. So is there any question? So somebody had asked me if I should change the kg to be newtons. No, we are dealing with the mass. The equation is dealing with the mass. So the mass is already in that particular direction. So the mass must just be in kg. It's already in SI unit. So what matters is that everything should be in SI unit. The mass should be in kilogram. Acceleration should be meters per second square, per square second, that is acceleration. Okay, so once we have that, now let's talk about something else that comes together with this idea of momentum. We are now applying a force, of course, there's a change. But you see, the same thing is what normally happens when, let's say that you have a collision of something. Let's say that there was an accident, for instance. We are going to look at this later on, but assuming that this thing was coming and maybe it approached a certain wall, there's a wall like that, then it bangs onto the wall. of course, you realize that there'll be some change in momentum. So that change in momentum, what is it? What does it have to do with us like that? We need to quantify the effect of that particular change. Does it have any change on us? So that if you know that if the change is big, what does it mean? If it is too big, if it is too small, and then what can we use? Or maybe if it is about taking precaution, what can we do to take precautions like that? So there's something that comes together with this, and that is what we call the impulse. It is what we call impulse. 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 So assuming, suppose that something, let's say that maybe you have a hammer, and the hammer hits a nail, or you hit a wall with that hammer. So it just hit, then you withdraw. Because if there's a wall, the hammer will hit the wall, then you withdraw. Hit, then withdraw. You see, it will be just an action that takes a very short period of time, like that. So is it possible to know that effect, the effect on that, the effect that we are going to have maybe on that board, on that wall, when that force is acting on it for that short period of time, not for very long, that short period of time. Like when things collide, it just, the process, the action takes a very short period of time. Then after that, of course, the bodies will do another thing. When you are falling down, or maybe if you are walking and you hit a stone, you normally feel the pain instantly. And so that hitting doesn't take so long. You want to say that you are hitting a stone by the roadside for like 2 minutes. No, it's always like few seconds. You just hit the stone and then you feel the pain immediately. So that effect, that result, that effect of that force acting on you or on a body for a certain short period of time, that is what they call impulse. So it's just the result of that force, the effect of a force acting on a body for a short period of time. And that force is normally called the impulsive force. That force that acts. So impulsive force, you can define as the force impulsive force. Impulsive. So you can define as the force that acts on a body for a short period of time. Impulsive force. So this is a force acting on a body for a short period of time. Let me call it F. So it acts on a body for a short period of time, like that. So the effect or the impulse, so the impulse will just be the product of those two. The impulsive force times the time through which the force acts, like that. That will give us the impulse, the effect. And you realize that the effect will be great when, so this means that the effect will be great when the force is too big, and also when the time for the collision maybe is long. But then the focus is always not even that. The focus is always on the impulsive force, this force here. This is what is always in our main focus. So let me just write how you get it. The impulsive force should be that effect, which is the impulse, and then we divide this by time, like that. So from here, the force, of course, this force there, that now going to do the action, this force here, now is dependent on two things, dependent on the impulse and also dependent on the time, on the two things. Now I want us to see how we can modify the impulse that we are able to experience and see if there's something we can do to reduce this effect of this force. And maybe this time, is this something we can do? Of course, you realize that to reduce the impulsive force, you can just have the time becoming longer. And that's okay. The impulsive force will be reduced. But let's look for another way to represent this impulse so that we can see something you can modify so that you can reduce the impulsive force. And this is actually applied in most cases. If you look at how the vehicles, the bumpers, the vehicles are designed, if you look at those who do the high jumpers, there's a reason why that place is made soft for them as they land because of this idea, this equation. So go back to this so that we represent it in a much better way. We have that the impulse is given as the force acting on that body for a short period of time. And then from the Newton's second law of motion, F is equal to ma. So instead of having m here, we can have instead of having F, we can have ma times t, like that. And then A, which is acceleration law is given as v minus u over t. So you can have m, then times the A, which is v minus u, so over t times the time. And then this looks beautiful because you can cancel the t and the t and end up having m into v let me erase that. So you'll end up having m into v minus u, which you can just open up the bracket so that we see something, mv minus mu. Now, if you check this one here, it is something familiar for us. What is that? mv minus mu. What does it give you?
Change in momentum.
Change in momentum. Now, then we can now make a relationship. Let's go back and check. There's something we are there. So it means that then impulse can also be just found by saying that it is supposed to be the same change in momentum. So that's mv minus mu, just change in momentum, like this, change in momentum. So the impulse is basically change in momentum. And that now, if you go back here, and the impulse is also given as ft, so it allows us to also write it as ft, or because that is impulse, is also equal to mv minus mu. So this is important because there are some problems you let's solve depending on what you have, like that. How is this practically applicable? How is this practically applicable? Look at this. If the impulse is mv minus mu, it means that the impulsive force can be decreased by decreasing this amount. And how do you decrease this amount? You simply ensure that. But how can you decrease this change? This one here, this quantity here, the value of this change in momentum. What can you do to decrease its value? Assume that the mass is constant, of course, the body has to be constant. In case of an accident, you want to reduce its value for an accident. What do? You only need to modify this. This is the only thing you can work on, this one here. Because in an accident, in one way or the other, you may end up coming to a rest. So U is already fixed for you, it is 0. Mass is the body of the vehicle plus the occupant. So that's already the mass. But you see, the velocity is the, which is fixed. This fixed, V is 0, final is 0. So U is what you have originally before the accident. So you can always change that. You can decide to move faster or move slowly or move averagely. If you're moving at a very high speed, very, very high speed. Now, can you look at the big damage that's going to happen here? If you move at a very, very high speed, it means that the change momentum in case of an accident will be too big. And because of that too big change momentum being too big, if you look at our equation here for the impulsive force, so the impulse, if the change in momentum is big, the impulse becomes big. If the impulse is big, the impulsive force becomes great. There's high chances you will die. And not only die, but also the vehicle will be damaged beyond repair. So that is how powerful it is. It is good to take precautions. So normally that's why at times there are always sometimes some precaution that is taken. The bumper is there, the airbags are there, all those things just to try and ensure that you are protected from this impulsive force in case of an accident. Now that we mentioned the quantity, there's something I didn't mention. I didn't mention its unit, of course. So the unit you can see here, it has 2 units. At least now you can see that there will be 2 units here possible. Impulse is F times T. So this one gives us a unit of Newton second, because just force times time. This Newton times second, which is Newton second. Then also the same impulse, we have said that they change in momentum. So we can also give it as, so apart from Newton second, not Newton per second, Newton second. Apart from Newton second, it can also be the unit for momentum. The unit for momentum. So it can also be given as kilogram meter per second. So you can talk of 1 Newton second is equal to 1 kilogram meter per second, because they're basically the same thing. And of course, there's something, if you are to draw a graph, sometimes we'll always draw for you this graph, so you guys go to know. If you are to draw a graph of force against time, like that, we can ask you some questions from it. But what you should see is that if you have force times time, then probably the area under this graph will give you something. Suppose the graph looks like this, for instance. Then if you are to find the area under this graph, if you forget about the constant of a half, let's look at base times height, which is a half time t times f, which is the same as half ft. You look at that ft, it is basically momentum. I mean, it's basically the same as impulse, because that is the definition. So this one here. So if you focus on this, you basically see that is the impulse. So from there, once you know the impulse, you can find other things. Maybe you can find the, because from the change in momentum, you can find the impulse. You can even find the mass of that body. It's possible. The mass of a body. You can find many other things. There are the questions you can solve from that, knowing this idea. So what should we include? We should know that the impulse is also the same as the change in momentum. That's one takeaway from change in momentum. So that we can talk of Ft equal to mv minus mu, and all of those other small stories that we have also mentioned. So that tool is very important if you are to solve many problems involving that. Maybe something also you have to keep in mind is that when dealing with the momentums, direction matters a lot. So if you have one body moving this direction, the other one moving in the opposite direction, this will become the positive, this becomes the negative. If all of them move in the same direction, you're allowed to take them all as positive. But the convention matters a lot, because velocity is a vector, momentum is also a vector, like that. So seems like our time is up. But then what I would want you to proceed with at your own free time, once now that we have mentioned the idea of momentum, go and check now on the law of conservation of momentum, law of conservation of linear momentum. That the momentum before, of course, before collision must be equal to the momentum after the collision. In other words, we are saying that the total linear momentum must always remain constant if the bodies are colliding. And then from there, you go and check on the types of collision, elastic and inelastic. Of course, elastic, we know that we conserve both kinetic energy and momentum, while inelastic, we only conserve momentum. Where the bodies now you move after colliding, they can be together and then move in one particular direction, like that. So you can practice and check on those so that the remaining things becomes Newton's third law and then the friction. So I want to stop there unless there's a question. No. Now, there are ideas here. There are things that people want me to cover. Actually, I have a class from 11. There's a class waiting for me to join in. So I may not cover all this, but the lift moving upward or downwards, that's very direct. I don't have time to maybe derive for you the derivations. It's important when you understand by deriving. That's always the best way. You understand by deriving them. But if you don't have the time to derive, you can always just have the equations that are there always. Just what you need to know is that when the left is moving upwards, of course, you will always feel much more weight, of course, that is pressing on you when the left is moving upward as an acceleration. So that one tells that the reaction force that will be measured will be mass into bracket, the two acceleration, the gravity plus. So that's the difference. When the left is moving upwards, you add the accelerations because so that you can get a much greater reaction than you normally feel. When the lift is moving downwards, you normally feel lighter. So you take the difference of the two acceleration. That is the gravity minus the acceleration of the lift. When the lift is at rest, the reaction is just the normal weight. That is mg. So that is the idea of the lift. Then the idea of elastic and elastic collisions. So for elastic, we say they just conserve the momentum. So the linear momentum before collision must be equal to the linear momentum after the collision. And also, because it's elastic, we also conserve kinetic energy. So kinetic energy before collision must be equal to the kinetic energy after the collision. So just add the two of the two bodies before, then add them after the collision. When you're dealing with inelastic collision, where the bodies fuse together, in that case, the equations will be this. So if the bodies fuse together, the momentum of the first body before collision will be that plus the momentum of the second body before collision, like that, then is equal to, because the bodies will fuse together, they remove the common velocity v. So it will be their masses added m1 plus m2 times that common velocity of v that they're moving with. So this is the equation we're dealing with in elastic collision, perfectly inelastic collision. Perfect inelastic collision. Kinetic energy is not conserved because some of it is lost in form of heat, light, and sound. I mean, heat, sound, deformation, and all those stories. When dealing with this for inelastic, when dealing with elastic collision, we conserve everything, and therefore it will be, and things, the bodies may fly apart and move in different directions. So you talk of m1 q1 plus m2 u2 should be equal to m1 v1 plus m2 v2, like that. So the momentum before, momentum before, and then momentum after equal the same as this and that. So they're not difficult things. Just take your time and read and revise. You'll be able to understand them. So if you don't mind, please allow me stop at that point. So I think I've responded to those who have the questions, so that we can stop. Sawa. So I think let's stop at that point. I'll stop here. Then later on I'll end the meeting for all.
Thank you.